So here, since we're going to continue to need more space, guys, I'm going to stay out of the image a little bit longer. Here we're going to say a sample of radon-222 has an initial alpha particle activity, so just think of that as your initial concentration, of 8.5 times 10 to the 4, that should be a superscript, DPS, which means disintegrations per second. So basically it's breaking down by that much per second. After 7.3 days, its activity A is 3.7 times 10 to the 4 disintegrations per second. What is the half-life of radon-222? So again, we're dealing with first order kinetics here, but now it's just first order radioactive kinetics. So here, it's going to be ln nt equals negative kt plus ln no. And here they're asking us for half-life. Now remember, for first order, half-life was half-life equals ln2 divided by k. And here we're going to say that ln2 is the same thing as 0.693 when you punch it into your calculator. They're asking me to find half-life, so what I need to find is k. So remember, we're dealing with first order processes because radioactive decay occurs by a first order process. So it has the same exact half-life whether you're dealing with radioactive systems or not. So all we got to do now is just plug in what we know. I tell you that initially, this is what you have. So this is your initial concentration. Then we're going to say here that this is your activity after a given amount of time, 7.3 days to be exact. So that represents your final concentration. Equals, we don't know what K is. That's what we're looking for, so negative K. Time is 7.3 days. Now remember, because your time is in days, that means your K will be in days inverse. They have to agree in terms of time. So if K is in minutes inverse, for example, time has to be in minutes. They have to agree. All we got to do now is separate just the K by itself. So what we're going to do next is we're going to subtract ln 8.5 times 10 to the 4 from both sides here. So this gets taken out. Over here, it's going to give me negative 0.831733. And that equals negative K times 7.3 days inverse. Next, we want to just isolate K by itself. So we're going to divide out negative 7.3 days from both sides here. Okay. So the negative gets canceled out, and the 7.3 days gets canceled out. Now, because your days is on the bottom, when we find K, it'll be in days inverse. The negative and the negative cancel out, so I have 0.114 days inverse. Those days inverse, I just plug in over here, 0.114 days inverse. And because days is on the bottom here, when I find half-life, it's just going to be in days because I'm bringing it up back up top. So here it'll give you 6.08 days. Now, we might be talking about radioactivity now, but fundamentally it's still the same thing when it came to chemical kinetics. We're dealing with a first order process, so we're using in a sense the first order integrated rate law with the half-life for a first order reaction. If you can just see it as that, it's the same exact things that we've done earlier before in the earlier chapters. Remember that and just apply it so that you can get through problems like this. Here, instead of talking about molarity of our reactant, we're talking about activities, we're talking about disintegrations per second. It's the same thing. Just apply what you learned earlier to what we're doing now.